In this video, let us talk about alternating current, or AC as you may call it. So what is alternating current to start off with? Well, you know about simple current, which is the flow of electrons, and up until now we've been dealing with direct current, or current that only flows in one particular direction. So here I have a very simple I don't think I should call it a model, but whatever this is, I have a simple arrangement to explain you what the difference between direct current and alternating current. So direct current is, so for example, let's say this is a simple path here, a closed loop, closed path, similar to the path of electrons in a closed loop, in a closed circuit. So let's say this is my closed loop or the closed circuit, and these table tennis balls represent the electrons in the current carrying wire in the loop. So in a direct current, what we have, we obviously need a battery. So let's say my hands are will act as the battery, and I can have any electrical device such as a bulb or a motor that can be driven by the current. So what essentially happens is the battery just simply gives the electrons energy. Obviously it is electrical potential energy in case of a circuit, and this analogy is not perfectly it's not a perfect analogy, but yeah, I hope you can visualize what's going on. So the battery gives the electrons some energy, out of which some of that is the kinetic energy or the energy to move, and the rest of it is majorly the electrical potential energy that can be used to do some work. So in direct current, when we have DC, the battery pushes the electrons in obviously in only one particular direction, and the electrons keep on moving in that particular direction. That is simple direct current. Now what is alternating current? Well, as the name suggests, alternating current is a current that whose direction keeps on alternating, which means it keeps on changing. So let's say for the first 1 second, the battery pushes the electrons in this direction, anti-clockwise direction, and then after 1 second it switches its direction, switches the battery terminals, and now the battery will push the electrons in the other direction for 1 second. Now after again 1 second it switches its direction. Let's say I switch the battery physically, the terminals, and it'll start pushing the electrons in the other direction. And so this is what will continue. The battery will first push it in one direction, then switch and push it in the other direction, and so you get this kind of motion of electrons. Obviously it's not exactly what's going on, but yeah, it's a good way of visualizing alternating current. Now that is what alternating current is, and what direct current was, the difference. Now coming on to the actual way of how alternating current is generated, and even before that, let us even understand what current is and why do we really use what is the real use of electricity or the flow of electrons. Why do we really need electricity? Well, electricity is nothing more than a medium of transferring energy from one place to another place. Now that would seem very awkward, because for us electricity is energy, and yeah, to some extent that is true, but actually electricity or the flow of electrons is nothing but a convenient way of transferring energy from one place to another. Say you have a hydro power plant that generates electricity from water, from the motion of water, from the potential energy stored in water, and you have to somehow transport or transfer that energy from the hydropower plant to your houses. How do you do? One way is to store it in a battery and transport that battery in some trucks or is in any way of transport, and bring it to houses and give those batteries. But that is not a very efficient method, and that is where we use electricity. We connect the power plant to your house using a wire, and inside that wire, so this could be that wire, all wires are essentially the same, they're nothing but metal conductors that have electrons in them, and at one place, let's say this is the battery, so I have to transfer the energy from this place, which is the battery, to let's say this place where I have a bulb. So even in a small circuit, I'm actually using the wires to transfer energy from this place, which is the battery, to the bulb. Now how do I do that? The battery here keeps on pushing the electrons. So let's just talk about direct current for now. It pushes the electrons, it gives those electrons energy, and those electrons I am giving energy to this electron will repel the next electron, and so on and so forth, and this chain effect actually transfers the energy throughout the whole circuit. And this way, however long the circuit may be, you can actually transfer energy from this place to the other place through this chain effect. So it's the chain effect that really matters in electricity, that really makes the energy go from one place to another, and that is what we really need electricity for. Now if we talk about direct current simply means that the chain effect is happening in only one particular direction, by which I mean this electron repels the next electron, and this chain effect happens in only this particular direction. In alternating current, where the direction of the current is alternating like this, the chain effect for some time happens in one direction, and then it simply switches its direction, and the chain effect happens in the other direction. But one thing to keep in mind is that even if the direction of the motion of electrons is alternating, I am still able to transfer the energy from this place to that place instantaneously. And that is a very weird thing about current. The actual velocity of electrons might be very slow in a circuit. See, the velocity of the balls is very slow. They're not moving very fast. See, but the chain effect that goes from this place to that place, that happens very fast. And even in circuits, you might have a very long wire traveling hundreds of kilometers, and when you switch on the circuit in one place, the current would, obviously the electrons would move much more slowly. So you can look up the drift velocity of electrons. That's not very high, but the effect that the chain effect, that travels very fast. And even if the wire is hundreds of kilometers long, as soon as you switch on the circuit from one place, you would almost instantaneously get the circuit to be flowing. So you can see that as soon as I start pushing the electrons from here, the balls in this case, I get the chain effect to reach there. See, and so I can also have an alternating current, and an alternating current can also make the energy transfer, or make the energy reach from this place to that place equally easily. One more question that you might have in your minds is that, isn't AC a very inefficient method of transferring power from one place to another? Because you have to, so every time you switch the direction, you have to slow down the electrons and accelerate them in the opposite direction. Isn't that a very inefficient method? Well, the answer to that is no, because even if you remember, even in direct current, what we have is, we have these nuclei, these fixed nuclei, and with their bound electrons, and you have the small free electrons that are responsible for conduction, and these electrons are already buzzing in all different directions, and they're constantly hitting these nuclei and moving in random directions. Now as soon as you apply some electric field, they begin to drift in that particular direction. And how it really happens is, it's not this very smooth flow of electrons that you might imagine. It's not this kind of flow, but it's rather a very messy kind of a chaotic situation where the electrons is moving in various random directions. It is hitting the nuclei present there that are fixed there, so it may move in that direction, hit it, then move in this direction, hit this in that direction. And due to the net electric field that we have due to the battery, it would begin to drift. So although it is moving in all random directions, the net movement would be in the direction of the electric field, right? So, and if we look at the idea of relaxation time that you've already studied, you know that the electron accelerates under the electric field, and it gets some time to accelerate before it undergoes the next collision, let's say with this particular nuclei, loses its energy, then again it accelerates again under the electric field, due to the electric field, accelerates for some time, hits the next nuclei, and loses its energy. So it's a sequence of acceleration, collision, losing energy, acceleration, collision, losing energy. It's a sequence of that, and it's a very irregular movement. So even if, let's say, it accelerates in this direction, so in direct current accelerates in this direction, a net acceleration in this direction, hits the nuclei, loses energy, then again accelerates in that direction, hits this nuclei, let's say, loses energy, and then again accelerates. That's DC. Now in AC, it may accelerate in this direction, hit this nuclei, loses energy. Now by the, let's say by this time, the polarity has switched. So it would simply accelerate in that direction, maybe hit this or lose energy, it loses energy, and then maybe accelerate in the opposite direction. So it's so already the motion is very chaotic. What changes in AC is just that the direction in which the electrons accelerate after each collision, that might change after a fixed period of time, which is called the time period of the particular alternating current. And yeah, if you think about it in this manner, it doesn't seem so inefficient. Yeah, so now that is also done, why alternating current is not so inefficient. And yeah, we'll see in the coming videos, coming topics, that alternating current does have some benefits over direct current, and yeah, we'll look at that later. Now if I look at the mathematical aspect of this, we know that alternating current is generated by an alternating current generator, an AC generator, which is nothing but a coil moving in a magnetic field. Yeah, I hope you remember that from the previous topics. So if that is unclear, you can watch the Khan Academy video on that, on AC generator. But yeah, here let us focus on the mathematical aspect of how we represent alternating current. So from there we've seen that the rate of change of flux d phi by dt, I hope that is visible to you. Yeah, d phi by dt, that equals, so what is flux through a given coil? Well, it is the area of the coil times the magnetic field through the magnets in the AC generator times cos theta, and theta is the angle between the coil's area vector and the magnetic field. I hope you remember that. I won't get into too much detail because it's already done. And you can represent theta as the product of the angular frequency omega times the time. Now what is angular frequency? It is the number of radians that the coil covers every second, right? That is its angular frequency. And number of radians, so omega is number of radians. I'll just write that here. Omega equals number of radians covered in 1 second. So divided by the number of radians divided by the time taken. So let's say it covers 5 radians in 2 seconds. So 5 by 2, that is its angular frequency. And if you multiply that by the time, let's say it covers 5 radians in 2 seconds, and you multiply that by 2, so the 2 and the 2 cancel, and you're left with 5 radians. So if essentially I multiply the angular frequency, this is angular frequency, if I multiply the angular frequency, I'll just write it this way, this is the angular frequency. If I multiply the angular frequency with the time taken, what I get is this t and this t cancel out, and I simply get the number of radians, or theta, right? Theta is radians, number of radians, so I get theta in radians. So I can represent theta, I can replace theta by omega t, because I just saw that the product of angular frequency omega and t, time, is theta itself, right? So yeah, that is how I represent this. And obviously I need to write it d of the whole thing by t, so it's a derivative of this whole thing. And if I just differentiate it, d phi by dt is the EMF, the rate of change of flux is the EMF, and I can just simply shift the a and the b outside of the derivative, because the area does not change, the magnetic field does not change, they are constants, so I can just pull them out. I'm left with d cos omega t by dt. Now what is the if I can use the chain rule and all that stuff to find this out, but I can use the chain rule, but a logical method would be, so okay, first let me just apply the chain rule and show you how it just happens. AB remain AB. Now I can write this as d cos omega t by, so what I can do is I can simply write it as d omega t into d omega t upon dt. So what I've essentially done is I have multiplied the numerator and the denominator with d omega t, so that should not make a difference. And now what this does is this makes my calculations easier. What I get is now the rate of change of cos omega t, so d cos something upon d that something, so I can also call that as d cos x upon dx. So that is nothing but the derivative of cos, which is sine. Yeah, so I get sine of whatever that thing was, and that whatever was omega t. Yeah, I'm running out of ink, but yeah, there you go. So I get AB sine theta times the rate of change of omega t, so d omega t upon dt. Omega is a constant, I can pull that out, and what I get is d omega dt upon dt, and dt and dt cancel out because the rate of change of time with respect to time is 1, and I am left with an omega there, so into omega, and the EMF equals AB, and I'll just write the omega here because even that is a constant in a given case, and sine omega t, and that is your EMF right there. And yeah, I forgot to write the negative sign here because the derivative of cos is minus sign, I believe. Yeah, there you go. But obviously for now let's just ignore the sign because the sign doesn't really matter. It's just EMF, it's just the polarity, and which is obviously already switching. But yeah, there you get the idea of it, and that is how we represent it. And if you still confused why does the EMF depend on this angular frequency, well, that is, first of all, it simply makes sense. What is angular frequency? It is the rate at which you are spinning your coil, and obviously if you spin your coil faster, you should get a higher EMF. That simply makes sense through the law of conservation of energy. Faster, if you move the coil faster, you are putting in more energy to move it faster, and if you're putting in more energy, you should get out more energy in the form of EMF, right? So if you move your coil faster, you get a higher EMF. It kind of makes intuitive sense to me too, and I hope it makes sense to you too. Now what you can do is, we know A, B and omega are constants, so we can just put them together in one giant constant, and we can call that, so let me replace the word EMF with voltage for now. I think we are more comfortable with the word voltage. So what I'm saying is, so what is this? This is nothing but, let's say this is my generator here. I hope that fits. Yeah, let's say this box is my generator here, and I have two wires coming out of it, and let's say I have a voltmeter here. I think I should connect it in parallel. Yeah, I have some resistance here just not to short circuit the whole thing, and yeah, I have an AC generator there, and I have a resistor just not to short circuit everything, and I have a voltmeter connected in parallel to it because that's the way we connect it. And now if I try to measure the voltage, so this V here gives me the reading of the voltmeter at any given instant. So let's say I pause the time right now, and this equation would, and if I put in the put in t there, the value of time, let's say at 2 seconds, and if I solve this, I get the voltage at 2 seconds. And because this is AC, the voltage would keep on varying. Yeah. And what does A, B and omega give me? Well, let's say at some given time, when would the voltage be maximum, so to speak? Well, it would be maximum. So this whole term here, A, B, omega, is constant, right? What changes is sine omega t. Only this term here changes. So when would the voltage be maximum? value to its maximum when this changing term gains its maximum value. And when does sine of anything gain its maximum value? Well, it gains its maximum value at 1. So the maximum value of sine of anything is 1, right? So that would happen when omega t or theta would be 90 pi by 2. And so let's say as some orientation of this coil, we get the theta as 90, and we get the we get sine of 90 as 1. So this whole term becomes 1, and if this whole term becomes 1, AB omega into 1 or AB omega simply gives us the maximum value of voltage. So this term here gives me nothing but the maximum value of voltage that I can get out of this particular generator. So instead of writing AB omega t every time, what we can do is I can simply replace those 3 letters with one constant called Vm. I think I should use a different color because I'm running out of ink. Vm, that looks good, yeah, Vm, and that is nothing but the maximum voltage that I can get out of this generator. So what does this equation tell me? This equation tells me that the voltage at any instant is nothing but the maximum voltage that I can get times sine omega t, and this whole term depends on the time at which you're finding the voltage. So it would vary like a sine curve. And yeah, in the next coming video we learn about how we represent it in waves and all that stuff. But yeah, this is the basic equation of voltage, and now you know why where this comes from. And yeah, this is the equation that we'd be following from now onwards. That's it for this video.